Let's take a look at problem number 2 in the Newton's Laws problems. It's a lot more involved here than the previous ones, but we're going to be using a lot of the same techniques. So, starting with letter A, we just want to find the magnitude of the normal force on the bucket when it's sitting at rest on the ground. Well, you don't even have to go through the entire free body diagram and drawing all the vectors and all that. You know what's going to happen, right? We got the weight of the bucket down. It's not doing anything, so the net force has to be 0, which means since it's pressing on the ground's going to press back up with the normal force, and the normal force is just going to support the weight, keeping the net force equal to 0, the acceleration equal to 0, and so without even showing any work, you can just reason out the normal force is going to be 27 newtons. Now, that's not always going to be the case, that the normal force is equal to weight. It'll certainly be the case in many problems, but you always want to be thinking, is anything else happening here? And in this case, nothing else is going on, so normal force just supports the weight. Okay, great. Let's go on to the much more interesting part here, where now the rope is attached to the bucket's handle, it's pulled up, and the bucket has an upwards acceleration of 0.88 meters per second squared. So now is the time we're going to do all the stuff I was showing you before with the free body diagram, starting with some information off to the side. So if you haven't done it yet, go ahead and pause the video. We want to draw the velocity, acceleration, and the net force off to the side, and then draw all the forces acting on the bucket. Okay, the point is that the bucket is going up and accelerating upwards, right? So that means we want to draw off to the side the velocity pointing up, and it's speeding up as it goes, so the acceleration is pointing up as well. And which way should sigma f be pointing? Well, as I said before, the net force and the acceleration always point the same direction. So if it's accelerating up, the net force points up as well. And then before we do anything else, we want to assign a positive direction, and I hope you can see that upwards seems to be the best positive direction. So again, this positive sign near the velocity is not saying only the velocity is positive, it's saying anything pointing up is positive. Great. Now let's show the actual forces. And what force do we start with? Weight. We always start with weight, mg, and you don't have to show any work for calculating. In fact, we've already done it before. We know it's going to weigh 27 newtons. Which way does weight point? Straight down. Good. So there's mg, pointing straight down. Fantastic. What other forces are acting on it? Well, in part A, there was a normal force, but that was because it was on the ground, on a surface. But now, it's not on the surface anymore. See, not every problem is going to involve a normal force. In this case, there's a rope attached to the bucket. And what sort of force is in a rope? That's going to be a tension force, right? So we can use that capital T symbol for that. Which way is that tension going to be pointing? Well, the rope is above the bucket, pulling it up, and so the tension is going to point up. Now, how should we draw that tension vector compared to the weight? Should it be equal in size to the weight, larger than the weight, or smaller than the weight? Pause the video and think it through if you're not sure. Well, our clue is this, that we know that the bucket is accelerating upwards, which means the net force is pointing upwards. Now, here's where some students get confused between net force and force. Remember, net force is the combination of all the forces. That means when you put all the forces together, which we haven't done yet because we don't know which way the tension is, how much the tension is, but when you put them together, overall, the vectors will combine to make an overall vector pointing up. That means that tension being the upwards pointing vector, it has to be larger than the weight, so that in the end, the net force points up, so the bucket accelerates upwards as it goes. And so we're going to draw the tension vector longer than the weight vector. Now, I don't know exactly how much longer to draw it, just draw it obviously larger, so that anyone look at this and say, oh yeah, I can see it. That tension is definitely beating the weight, making the net force up, making the acceleration up as well. It's a very visual sort of thing. You want to get in the habit of doing that. Okay, now, we are ready to move on to the next part. We want to find the actual magnitude of the tension in the rope. Now, maybe you figured out some ways to do this, but let's go through all the steps, because the very next thing you want to do is write sigma F equals ma. Always, always, always sigma F equals ma. And then the very next step is only to focus on the left-hand side of this equation. We're going to build up sigma F for this situation. And this is why we do the free body diagram. The free body diagram organizes all the forces there so we can see which forces to compare. In this case, we're comparing the tension and the weight. We've shown their direction, and we've shown their relative length, and we've established a positive direction. So here's what we're going to do. This is the way I want you to do it. You're going to look at each force on the free body diagram, and you're going to list it here with its proper sign based on the fact that we have decided up is the positive direction. So we see tension. Tension is pointing up, and up is the positive direction, so that means that's going to be a positive T. Weight is pointing down, but up is the positive direction, so that's going to be a minus mg, right? So positive T, because T is pointing up, and we call that positive, minus mg, because mg is pointing down, and up is positive. So here's what we're doing. We're saying that these are the forces that are going to combine to make sigma F, and the right-hand side is still just ma. So that's always the next step. After doing sigma F equals ma, you list each of the forces with their proper signs. Now, some of you may have seen other ways of doing this. Some ways are just always add all the forces and later put in their signs. And that is one way of doing it, but I'm going to tell you that after many, many years of doing this, I find students are most successful doing it this way. So I really strongly encourage you to do it this way by listing each force and immediately putting the proper sign on them based on the way they're pointing compared to the positive direction that you have already assigned. Okay, from here, now you always want to rearrange first. So we're going to add mg to both sides because we want to solve for the tension in the rope. So T equals mg plus ma. And you may say, aha, we've discovered the equation for tension. No, we haven't, because as it turns out, there is no equation for tension. The tension will completely depend on what's happening in the problem. There's no one way of finding the tension. This is just what happened in this particular case. And some students say, oh, every single time tension beats weight, I'm going to use this equation. I wouldn't do that either. Here's what you want to do. You want to draw your free body diagram, assign a positive direction, write sigma F equals ma, and that's the basic structure, the strategy for solving the problem. And then you combine the forces and see what happens, because if you try to memorize every single version of the different equations, you're going to drive yourself crazy. So don't do that. Just follow the routine. Okay, so at this point, if you want to put your numbers in, you can, because we already calculate what mg is, and we know the mass and the acceleration is given as 0.88 meters per second squared. Or if you want to get a little fancier with the equation, you might see that mass is common to both terms. You can actually factor mass to the outside and write it this way, which just means maybe some fewer numbers to push on your calculator. Totally up to you. You're going to get the same answer either way of 30 newtons. Go ahead and crunch the numbers, put the numbers in your calculator, and make sure you can verify. You're going to get 30 newtons, or since it's 2 sig fig, 3.0 times 10 to the first newtons. Okay, and certainly this agrees with what we originally asserted. We assumed that tension was larger than the weight to make the net force pointing up. We got a value of tension of 30 newtons, which certainly is larger than the weight of 27 newtons. Everything seems to work. Now at this point, let me just sort of digress for a second here and talk a little bit about this quote-unquote equation, T equals m times g plus a, because once again, well, two things. One, students may say, oh, now that's the equation for tension. Ooh, it's all fancy, pull mass to the outside. Still, no, this is not the equation for tension. There is no equation for tension. Now, here's the other major issue, which I know some students sort of fall prey to. Students say, oh, it says g plus a. That means, oh, we're adding accelerations. Let me be as clear with this as I possibly can. No. I'm going to do it again in case you missed it. No, we are not adding accelerations. It's not like the acceleration of the bucket is quote-unquote really 0.88 plus 9.8. That's not true. That's not what this equation is saying, even though it appears to be doing that. The acceleration of the bucket is 0.88 meters per second squared. That's it. That's it. That's the acceleration. You don't have to add or subtract 9.8 just because it's moving vertically. That's not what's going on here. The acceleration of the bucket is given. It's 0.88 meters per second squared. That's it. This g plus a is literally just an artifact of the algebra. That when you do the algebra here by putting all the proper signs in it and you factor mass to the outside, you have this term of g plus a. That is not telling you we're adding accelerations. We are not adding accelerations. We are adding forces. That's what sigma F equals ma says. You add, as vectors, the forces. As a result, the bucket accelerates at 0.88 meters per second squared. That's it. That's it. That's it. So if you've been thinking about it in any other way, you've got to get that out of your mind. You've got to erase it. It was wrong. You may have sort of convinced yourself it was right, but I'm telling you, it was wrong. The bucket's accelerating at 0.80 meters per second squared, and that's it. And the reason why I really harp on this is that if some students think, oh, the real acceleration is 0.88 plus 9.8, well, then you're going to think that's the acceleration. And then if you have to do something with it later on, you're going to get the problem wrong. The acceleration is 0.88. It really is. No joke. That's it. Okay, now let's move on to the next part here. Tension is reduced. The bucket continues rising at a constant speed. You want to find the tension in the rope, and I know the answer is given to you, so it's sort of given away, but you really want to think it through as to why this is happening. And the key here is that phrase constant speed. Hopefully you noticed that. Maybe you want to underline it or highlight it, because if it says constant speed, that means the acceleration must be 0. That means the net force must be 0. Now, does that mean the tension is 0? No, no, no. Maybe you're confusing net force with force, right? Net force is the combination of forces. The forces combine to make 0 net force. The tension is just one of those forces, meaning that if there's weight down at 27 newtons, that means there's going to be tension up of 27 newtons. Just balancing out the weight, which was the exact same situation we had in letter A. So some of you may be thinking, that means that tension is the same thing as normal force. No, that's not true. No, they're just happening playing similar roles, that they're counterbalancing the weights. In letter A, normal force balanced out the weight to keep the bucket sitting there on the ground. In letter C, the tension balances out the weight just to maintain its motion. Then some of you may be saying, wait a second, if the tension is 27 newtons up and the weight is 27 newtons down, how is the bucket moving? Well, that's because the bucket is already in motion from part B, okay? So in part A, the bucket was at rest on the ground, net force was 0, normal force balanced the weight. In part B, you pulled up on the rope without tension larger than the weight, getting it to speed up for some amount of time. And then, in letter C, you let up on the rope a little bit, so the tension just matched the weight, maintaining its motion. So it was already moving from part B into part C, and part C, you're just maintaining that motion for this 4.7 seconds. All right, let's go on to letter D. Go ahead, pause the video, and see if you can sketch out what the graphs will look like. Okay, let's take a look at the velocity versus time graph first, and we know that the motion is broken into two sections. There's the 1.3 seconds of acceleration, and there's another 4.7 seconds of constant speed, or zero acceleration. So the first thing you want to do is figure out what the final speed of the bucket is after the first 1.3 seconds. If you didn't do that yet, because we are going to put in some numbers on the graph here, just go ahead and do a quick calculation using some kinematics to find the speed of the bucket after the 1.3 seconds. Okay, so you can just use a little VF equals V naught plus AT, and it starts at rest, right? And from letter A is at rest on the ground, and it's accelerating for 1.3 seconds. What acceleration are you using? Should we use 0.88 or should we use 0.88 plus 9.8? Well, if you were paying attention, you know, because I was just discussing this, and this is where it comes into play, because the acceleration of the bucket is 0.88 meters per second squared. You should not be, quote unquote, accounting for gravity. That's already accounted for when we did sigma F equals ma. When you pull up with 30 Newton force of tension and the weight pulls down with 27 newtons, the net result of that is causing the bucket to accelerate at 0.88 meters per second squared. Okay, so using that times 1.3 seconds, we should be getting a final speed of 1.1 meters per second, 1.14 if you have a third sig fig, but we want to just sort of label that, you know, maybe label a little scale here of 0.5, 1.0, 1.5, and so the final speed is going to be 1.1 meters per second for the first 1.3 seconds. So what I'm going to do is I'll put a little dividing line there, what looks like about 1.3 seconds. All right, so what shape should the graph be here? Well, we know it's going to start at 0, 0, because it started at rest. At 1.3 seconds, it's going to be at about 1.1 meters per second. What shape will it be? Well, here's where you start to look at the connections among graphs. When you think about shape, you're thinking about what the slope represents, what the slope is doing. So this is a velocity versus time graph. What does slope represent on velocity versus time? That's acceleration. And in right before part B, it says it has a constant acceleration of 0.88. So we're looking for a shapeful graph that has a constant acceleration. In this case, that'll be a constant slope. What shape is that? That's linear. So it's going to be linear with a positive slope. Slope is acceleration. The acceleration is constant. That's a straight line, okay? From there on out, for the next 4.7 seconds, as it goes at a constant speed, that's zero acceleration, which means that the velocity is just maintained at the 1.1 meters per second until we get to the 6-second mark. So there it is. So it speeds up, and then it flatlines to a constant speed. All right, what about for the tension? Well, we know that in the first 1.3 seconds, we're pulling up with that tension that's 30 newtons, and it's a constant acceleration, so it's a constant net force, so it's a constant 30 newtons, and then we drop down to 27 newtons. So let's set a little scale here, maybe like 10, 20, 30. And again, for the first 1.3 seconds, we were pulling up with 30 newtons. So it's just going to be a constant 30 newtons for the first 1.3 seconds. And then we sort of instantaneously drop down to 27 newtons for the remainder of the time. Now, in reality, does this instantaneously drop down from 30 newtons to 27? No, of course not. Nothing can really do that because you have to go through all the force values in between. So in reality, it sort of slides from the 30 down to the 27. But, you know, we're going to sort of idealize it. By the same token, does this have a really sharp change from speeding up to not speeding up? No, in reality, there's going to be maybe a little bit of a curvature to that graph. But, you know, this being our first level course, we're just going to sort of idealize things and pretend we can have these instantaneous changes when in reality we know that's not actually going to happen. But again, this problem was really good review of how to do these sort of problems where we draw the information off to the side, we assign a positive direction, we draw the actual forces, we try to draw the lengths of the vectors proportional to the magnitudes, we label the kind of forces that are there. If we know the magnitudes, we label that as well. We do sigma F equals ma, we do this very next critical step, listing each force with its proper sign, and then you solve from there. That's the structure you're going to use for pretty much every problem involving multiple forces.